You can classify molecules as polar or nonpolar. This classification is extremely important because the classification helps to determine the intermolecular force. For example, if you're talking about a polar compound, which we'll get into more as we go into the semester, polar compounds can have hydrogen bonding, or they can have dipole-dipole forces. Now, in order for it to have hydrogen bonding, there is an additional criteria. Of an OH or NH bond. Technically, it's OH, NH, or FH, but because fluorine can only have a single bond to hydrogen, it's a molecule all by itself. But with respect to what we're going to be working with, you're looking for that OH bond or that NH bond. Now, nonpolar molecules can only have, there's a variety of names, but basically I refer to them as London dispersion forces. And what is a London dispersion force? And how does it work? First of all, the bonds within a molecule, the electrons, I should say, within that bond is always in motion. So they're, they kind of get along. If my head represents one atom and my feet represent another atom, for the most part, those electrons just kind of hang out in the middle. And yes, my hands are representing the electrons. But on occasion, those electrons wind up on one side of the molecule. Since electrons are negative, if they wind up on one side of the molecule, it causes that side to be temporarily negative. And if one side's temporarily negative, that means the other side is temporarily positive. So my favorite, and I think I actually described it this way in the background, but my favorite way to demonstrate what a true London dispersion force is we're going to do the wave. So we're going to start on one side and we're going to go through to the other side, doing the wave. And once it gets to the other side, we're going to come back. And then we're going to go back. And then I'll explain how that's related to London dispersion. So this group gets to start with the wave. Going hands above the head. 1, 2, 3. Oh. Okay. Now, how did that represent London dispersion? This group started something. Their electrons wound up on one side of their of their body. And because they did it, I'm trying to tell because I coerced you to do it, the next group did it. And because this group did it, the next group did it. And so on and so forth. And then it came back so that when this group got it, this group wound up going that way. That's what happens in London dispersion forces. It's temporary because as soon as your hands went up, where do they go back to? Back down. It's only temporary, but it starts a chain reaction. And that's how London dispersion forces work. Now, nonpolar molecules, that is its only option, is those London dispersion forces. So, now, if we're looking at it, alkanes, which consist of carbon and hydrogen only, are nonpolar compounds. So they have London dispersion forces. Okay, so that's the first thing you need to know about alkanes, is that the only thing they can have is London dispersion forces. The next thing we need to do is we need to talk about these intermolecular forces and their strength. The strongest intermolecular force is going to be that of the hydrogen bonding. Because the strength of intermolecular forces is all dependent upon how long does a positive exist. The longer the positive and the negative exist, the stronger they are. Well, an OH bond has a huge difference in their electronegativities. And therefore, there is a very strong positive and a very strong negative in an OH bond. And that's why it is the strongest of the intermolecular forces. Followed by dipole-dipole, which is still polar, and so it has a positive and a negative. Followed by London dispersion, which are temporary positive, negative. Now, if we're talking about a solid, and we want to melt it to form a liquid, what has to happen? Well, in this solid, we have extremely strong intermolecular forces. That's what makes a solid, is stronger intermolecular forces. In order to be able to make it into a liquid, we have to break some of those intermolecular forces. So in order to melt a solid, we've got to break up some of those intermolecular forces. To go from a solid to a gas, a liquid to a gas through the boiling point, you have to break all of the intermolecular forces. Now let's talk about that with respect to what we've learned. Hydrogen bonding has strong intermolecular forces. To pull it apart, I'm going to have to put a lot of energy into it. So in order to melt it or boil it, I would have to put a lot of energy. So it's going to have a higher melting point and boiling point. It's kind of like taking two people that are extremely strong and then holding on tight, and then me coming into that pair and trying to pull it apart. If I've got two strong sources, it's going to be hard for me to push them apart. So hydrogen bonding is a lot like that, where it's hard to push them apart. Now, dipole, I still have those forces in play, but they're not holding on very tight. They're just holding. I still have to put in some pressure to pull them apart. But I'm not going to have to put in near as much. So dipole has a lower melting point and lower boiling point than does compounds that have hydrogen bonding. Finally, we get to London dispersion. And London dispersion is like two people standing side by side. One here, one here. It's going to be easy for me to push them apart because there's nothing really holding them together. So it's going to be real easy to push them apart. So London dispersion forces have very weak, it's a weak force. And so it doesn't take very much energy to shove them apart. Since it doesn't take very much energy to shove them apart, they're going to have low melting points and boiling points. So if we go back up here to the strength, that means that this is higher melting points and boiling points. And it goes down so that you have lower melting points and boiling points. Methane has a boiling point of negative 164 degrees Celsius. Ethane has a boiling point of negative 87 degrees Celsius. Propane has a boiling point of negative 42 degrees Celsius. And if we get to pentane, which is the fifth one in line, it has a boiling point of 36 degrees Celsius. Octane, and yes, I'm skipping some. Octane has a boiling point of 216 degrees Celsius. So because these alkanes only have London dispersion forces, that's why they have fairly small to very small or low boiling points and melting points. Now you may go, okay, as we went up, what's going on? So with methane, we're separating two small molecules. If you're talking about, but if you're talking about octane down here, it's 8 carbons long. So you're talking about much longer molecules. So in other words, the reason that these have different melting points and boiling points has to do with this, the amount of energy in between those molecules. Methane has just a little bit. So it takes a little bit of energy, but not a lot. Whereas once you get to octane, because the molecules are much longer, it's going to take more because the hydrogen bonding intermolecular forces are stronger. Some other things about alkanes besides so what can we say what should we say to finish this out? Alkanes have low melting points and boiling points because they only have London dispersion forces. The melting point and boiling point increase as the number of carbons increases. Because there is an increase in London dispersion forces. With an increase in carbon. Some more details is that these tend to be mild in odor. Now you may go, but that is counterintuitive to what I know about propane gas. If anybody's ever smelled propane gas, like to heat a building, or propane that may be used to light a camp stove or something like that, propane has an odor. So why are we saying that it has a mild odor? What you're actually smelling in that propane gas is actually an additive. We actually add additives so that we can smell the gas and know when it's leaking. They are colorless. Because they are nonpolar, they do not dissolve in water. In fact, if you've ever pumped gas and it was raining and a little bit spilled, you would notice a puddle on the top of the water because the two can't mix. Now, one important thing that we're about to talk about is they are flammable. Propane is an example. We use it to heat homes. We use it for campfires. Butane is another example. Butane is in lighter fluid. Octane, a car can go boom if you're not careful. So, any questions about their properties and why? We're going to use this same theory throughout the semester as far as that, what type of force does it have? Is it strong? Is it weak? So we're going to come back to those intermolecular forces, and I'm not going to go into as much detail every single time as I did this time. But we're going to come back to it with every single type of functional group we talk about. We're going to talk about how the intermolecular forces alters the physical properties. Okay, so the next thing is the reactions of alkanes. Alkanes can only undergo two types of reactions. The first type of reaction it'll undergo is going to be combustion. And the second type of reaction it'll undergo is halogenation. With combustion, you're going to take your alkane. You're going to add oxygen. And if you have a complete burn, you're going to get out CO2 and water. That is the combustion reaction. You add oxygen, you get out CO2 and water. Now, I'm not going to say that that's the only compound you get. You heard me say if it's a complete burn, because you can get other compounds out besides CO2 and water, but if it is a complete burn, you're going to get out CO2 and water. Now, let's talk halogenation. Halogenation occurs in a very stepwise format. The first step in halogenation is the same. You're going to take a halogen, and that halogen is going to react to give two free radicals. So in other words, the halogen dissociates to form two free radicals. Step number 2. Is that one of the free radicals is going to react with our alkane, which I'm just going to use methane because it's the simplest of all alkanes, but all alkanes will do the same. And what's going to happen is this free radical is going to go in and it is going to tear apart that bond. So one of the electrons from the hydrogen carbon bond is going to go to make HCl. And the other hydrogen from the carbon hydrogen bond is going to go to make a new free radical of CH3. Now this CH3 with its free radical is going to go combine with the other chlorine free radical. There's a multitude of possibilities. It could take another chlorine molecule. Let me rewrite that. And it can go in and it can split up that chlorine molecule to make CH3Cl and another chloride free radical. That chloride free radical can react with our HCHClH and pull off a hydrogen, and you're left with HCl plus a CH2Cl free radical. The CH2Cl free radical can react with another Cl2 to make CH2Cl2 plus another HCl, or excuse me, another Cl minus, or Cl free radical. And it can keep going. So again, let me just back up now that you have it written and we can actually discuss it. Step number 1 is to take a Cl-Cl bond and break it up to make two free radicals. All a free radical is, folks, is it's a compound that has an electron that is not paired. That's what a free radical is it's an element that has an electron that isn't paired up. Once you get your free radical, it can work with a alkane. Now I used methane, but I could have used ethane, I could have used propane, it does not matter. It just works with an alkane. And the way it works with an alkane is the free radical rips off one of the hydrogens. It just yanks the hydrogen away. And that's where the HCl comes from, is from this chlorine ripping off that hydrogen. Now, we have to keep this going, so we have a free radical that's made. That free radical can then react with another chlorine, and literally it rips off one of the chlorines, leaving CH3Cl plus a chlorine free radical. The chlorine free radical can react with another hydrogen and rip it off, making HCl and another free radical. And this process just keeps going until you have halogenated every single location there was a hydrogen. Or until there's a termination step that occurs. So again, this process can keep going until you've halogenated every spot where there was originally a hydrogen, or until a termination step occurs. The termination step could be that two chlorine free radicals come back together to make Cl2. If you don't have a free radical, the reaction's not going to continue. Or you could have a chlorine free radical react with a CH3 free radical to make CH3Cl. Or you can have two CH3 free radicals react together to form CH3CH3 in this case. So the termination step, if you will notice, in all three instances, the termination step is two free radicals come together. The termination step is two free radicals coming together. What I want to draw your attention to, and this is going to be useful in every single chapter, we're going to go over reactions. In every single chapter, at the back of the text, at the back of that chapter, there is a thing that says summary of key reactions. That's going to be what you need to make. If you're one of those that makes flashcards, that's what you need to make flashcards of. Again, it says summary of reactions. So this is a very nice summary that I would use. And it'll be very useful, especially moving forward. This chapter is not as bad. It has two reactions. Halogenation, where you replace a hydrogen with a halogen, and combustion. This one is on page 397. Now, if you want to see the reactions as I tried to draw them, they did a better job of it. 387 and 388 are, they'll show you the stepwise halogenation of methane. And they'll also show you the termination steps. Okay. Now we're going to talk about cycloalkanes. Cycloalkanes follow the formula of CnH2n. Basically, these are compounds of carbon and hydrogen only. That are cyclic. Here, I have a cyclic hexane. It's called cyclohexane. Basically, it will follow the formula of CnH2n. So it is C6H12. And it's just an alkane because it consists of nothing but carbon, which is the black balls, and hydrogen, which is the white balls. It is nothing but carbon and hydrogen, just like we've been talking about. So it's still an alkane, but it is in cyclic form. Now, let's talk about drawing and naming. For drawing purposes, you're going to use line structures. Very rarely are you going to see it written as a structural formula. Most of the time, we're going to see it as line structures. And that's because it gets very chaotic if you try to draw every single atom. So a lot of times we'll use line structures to make life easier. Now, for naming. The process is the same as with alkanes, except the cyclic structure is the backbone, the main chain. Now so step number 1, is to use the cycloalkane name as the parent. So if it's 3 carbons, it's cyclopropane. If it's 4 carbons, it's cyclobutane. Cyclopropane and cyclobutane are pretty unstable. The first real stable one you get is cyclopentane. And then you can get cyclohexane, cycloheptane, cyclooctane. They're harder to draw, but you can have them. Step 2. Is to identify the substituents. And in this case, you start numbering. The cycloalkane. So that the substituents have the lowest number possible. So for example, if I had this structure right here, I would number this one 1, and I would go in reverse because I'd want to make sure my substituents got the lowest numbers possible. So this would be 1 ethyl, 3 methyl, cycloheptane. I mean, cyclohexane, excuse me. Folks, in other words, it's the same as what you just did with alkanes. You identified the longest chain in the alkane. Well, the only difference is now it's obvious who your parent has to be because it's got to be the cyclic group. And then you're going to name your and then in the last one, you chose your numbering system so that your substituents had the lowest numbers possible. You're doing the same thing. You're making sure your substituents have the lowest numbers possible. So it's the same process as before. It's just now we're in a cyclic structure. We're telling you what the parent has to be. It has to be the cyclic structure. Yes.
So would it be long if we start numbering from methane?
The reason we start with the ethyl instead of the methyl in that one is because ethyl is alphabetically lower. Any questions? That finishes chapter 12, which was my goal for today. So let me, actually, I don't know if I want to stop broadcasting. No, I don't. Now what we're going to do is work on the lab. If you have the lab done, you can turn it in and leave. If you don't have the lab done, I'll help you figure out how to do isomers. the key to isomers, folks, is they can't have the same name. They cannot have the same name. If you wind up drawing two structures and they have the same name, they're the same compound. Starting in California. Oh, thank you. Yeah.
I normally have to pick it out, but I was sick all last week and so it was a big I did that.
Okay. I'll be in my office or across the hall in the lab. I have 2 labs after this. That's why I have no office hours on Monday, as I go from 9 to 5. So. Okay, so the first one's always the easiest. Just draw a chain. Now, what we're gonna do for the next one is we're gonna take off one of our carbons and we're gonna move it around. So right now, this one is hexane. Now we're gonna take that carbon off. And if we take that carbon off the main chain, there's only 5 left. So now you move that 6th one around. So it could go here. If it goes there, now we have 1, 2, 3, 4, 5. So this is going to be 2 methyl pentane.
Does it matter which carbon we put it on?
No, I mean, I'm fixing to move it some more. So I just started with one of them.
Okay.
And now my original carbon that I started to move is this one. I'm going to move it again. But this time, I'm going to put it on the center one. And when I put it on the center one, I now have 3 methyl pentane.
So as long as the words can be the same, but the number, as long as the number's different on the words.
Well, as long as the number's different, the word is different. Now, it's tempting to keep moving it and put it here. But because you always number so that it has the lowest number possible, this is also 2-methyl pentane. So what you just did is this one and number 2 and number 4 are identical. So this is not an isomer. So instead of 1, now I'm going to mess with 2 of these at a time. I've done all I can with 1. Now I'm going to do 2. So if I do 2, that means I'm going to have a backbone of 4. Now, you can move them so that they're on the same carbon. Or you could move them where they're on different carbons. So this would be 2,2-dimethyl butane. But I could also move them so that they're on different carbons. And that would give me yet another combination.
Due to ethyl propane. That's how they come out.
No. Because number it so that you find the longest chain.
Okay, yeah,
It's actually a pentane.
yes.
But that's a common mistake. You got to go back and find the longest chain. And that should be the first 5. That should be the 5 of the first one. You just need to name that last one that I gave you. Now I'll let you work on the other one and I'll help out. Did this help in figuring out how to play with isomers? Take one off and then take 2 off and